Hi, Mitadru. Let's get started.
Okay, so good morning, everyone. My name is Mitadru Datta from CellStrat AI Lab and IIT Kharagpur, and I'm thrilled to be here today to host this webinar on Stable Diffusion. As you may already know, the Stable Diffusion is a crucial concept in many scientific disciplines. So thank you for joining us today, and whether you are a researcher or a student or a professional, I think this session would provide you valuable information on the topic. So we will first start by understanding what exactly happens. So in this algorithm, AI basically creates an image art from a text prompt. Now the prompt, instead of being a text, can also be an image, and we will see in some of our later extensions that it can also be some other signals. So one of the distinguishing factor for this stable diffusion algorithm is that it does not lose the semantic information of the data. So what does that actually means? We will try to visualize that. So from this is the Imagen by Google. You can see there is a text prompt. So the input is the transparent sculpture of a duck made out of glass. The sculpture is front of a painting of a landscape. So this is the output which is given by Imagen of Google. So what exactly happens? The input might also be an image, and if we give input of one image, we will get an output of the other image. The output image is produced as a reference to the input, and you can also see that the semantic information of the image is more or less conserved. It has not changed. So this way, AI creates an image art from an input image. So this is not just limited to 2D images. The latest diffusion models can also create 3D view of models. The models from a text prompt, you can just see the models from all angles, and some of the research is being conducted on things like if you give a text prompt of an human walking and picking up an apple, then the output will be a 3D model of a human actually walking and picking up something. So the area of research is something like this to this level nowadays. And many other applications from the fashion industry to medical imaging that we will see later in the stable diffusion extensions. So we will go into the details of how exactly it happens. So first of all, let me give a basic outline of what exactly happens. First, we take input images. Now, this input image might also be generated by some text, or it might also be generated by some maybe signals, maybe brain waves, and a lot of other things. And then we can keep adding some Gaussian noise to it. We treat each step of the noisy image as each timestamp, and the forward process would then look something like this. This is our image which contains no noise, and then we keep on adding noise slowly and steadily until in our final result we get a complete Gaussian noise. And now you might also remember that a complete Gaussian noise is represented by a normal distribution whose mean is 0 and variance is 1. So this will be our general signifying thing, that t equals to 0 we will take as the complete correct image, and let t equals to capital T, which has some value, we will take that as the complete noise. Then what we will do is that we use a unit architecture here as our machine learning model, and we take the noisy image from different timestamp and fit it into the model. The model then predicts now of course the input to the model might be many images instead of one. So we take many images from many different timestamps. We use some attention modules. We will exactly see how that happens. We also use something known as positional encoding. Again, the complete math, I am going to explain that. And then we predict the noise from our neural network model of unit architecture. And that noise is then slowly subtracted from the combination of images to produce the final output image. Now you must have heard of something known as image inpainting. Now that
So,
is,
Mitadru, so you are trying to predict noise from image
yes,
and then reverse it, produce image from noise.
yes,
So the idea is to eventually have a decoder which can generate image from noise,
yes,
right? Okay, fair.
sure. So first we will convert the image to some latent variables, which will be basically done by the encoder, and then the model will act, and then the decoder will also come into picture. So one of the important application you must have heard is image inpainting. That is, it completely separates something out of an image. Now, one thing you must notice is that uh, I am visible, right? So you can see my background is something else, and I am only visible here. But this is not exactly image inpainting. As I'm moving my hand over here, you can see something in my background or something in the outline of my which is visible. So it is not completely accurate. This is done using just a computer vision. A mask is created, and then using the OpenCV module, it is simply created. But if we use Stable Diffusion here, we will get really great results, which we are going to see in some of our later webinars. Now, there can be different strategies for adding noise. One thing can be we can add noise linearly and make it complete Gaussian noise. And we can also add noise as a function of cosine. So it is, in practice, it is also seen that adding noise as a cosine function produces better results. So what happens in linear noise is that slowly the noise, uh, we get Gaussian noise very quickly. The noise is added really fast, and as a result of which we do not get enough timestamps, and we basically lose the information of our original image real quick. So that does not happen when we add noise on the basis of cosine function. As you know, the cosine function always lies between 0 to 1. So the image is corrupted very slowly, and we get a large number of timestamps, and therefore the quality of our image while going to the backward process is observed to be the best. So before going into the architecture of encoder, decoder, and all, I would like to give you a recap of the variational autoencoder module. I'm assuming you know about this module. So just an overview, we take an image, we encode it using into latent variables, which is done using some advanced statistical techniques like factor analysis and also principal component analysis to reduce the dimensionality of the image into few pixels. And then we do sampling, and then we apply some reconstruction filter. So this is also known as decoding. Now decoding can also be done by some signal systems like sine sync reconstruction filter, which is basically sine x by x stuffs we are going to talk about some later point. So we get the final image. So this is what happens in a variational autoencoder, which is also known as VAE. So we will use the idea of VAE and construct our stable diffusion mode. So this slides need a lot of explanation. So how overview of the working flowchart. So as I told you, I will be using the idea of variational autoencoder, which in which an encoder is there, which basically convert our observed variable x into the latent variable. Now it must be very clear that this observed variable x might be a random variable function, which is basically, now the image is what? It is a 3D numpy array, which the first two arrays are the first two dimensions are the length and width, and the third dimension is 3, giving the RGB values. So it might be a random variable expressing that array. Now, Now, out of all the possible values of the NumPy array of each pixel of the image, we convert the observed variables into latent variables. Now, this latent variables is really fast and easy to work with. Now, as I told you, we might do many things here. We can do PCA, we can do factor analysis, and a lot of other things. Once we get our latent variables, we apply the forward diffusion process, which I will explain in detail. After applying the forward diffusion process, we will get a complete noisy image, which is given by ZT. And Z subscript T represent the complete noisy image. And as I told earlier, Z subscript 0 will represent the latent variable, which is the initial image after encoding that. Now, this noisy image or some other timestamps of this image, not necessarily only the last timestamp, will be fed into our unit architecture. Now, in our unit architecture, there will be some attention modules. So we will also see how this attention module actually works. So now for intuition, you can just understand it in this way, that using the attention modules, the neural networks has connections between the encoder and the decoder means within the first half and the second half of the processing, it can directly transmit data from one timestamp to another timestamp. And for the self-attention module, can transmit some other part of the data into itself. And we can also take some other text and image transformers and feed that. So this we are working with one image, and then we are converting all of the pixels and doing like this. Then now, obviously, our text prompt will have many words, and each of those words might represent many images. So other images from other transformer modules will also get the feedback from this denoising unit module. Okay, so once we are done with the denoising unit module, we predict the noise at each timestamp. Now we will simply subtract the noise and perform the backward diffusion process, which also will be clearly explained. So from ZT, we get ZT minus 1, and eventually we get Z0. And these are still in the latent variable form, right? So now we will use our decoder, which might be some reconstruction function, and then we can easily get our predicted variables. So this is the overview of how a general stable diffusion module works.
So, Mitadru, why do we need a denoising unit? I think in traditional latent diffusion algorithm, there is no unit, right? There is just forward diffusion to noise and then reverse diffusion to no noise or image. So,
Yeah,
unit,
so
why do we need unit here?
okay, so in some of the advanced research, it has also been found that some advanced architectures like CenterNet or Dreambooth performs better, but in the initial list, UNet was actually used for image segmentation purpose. So in the initial time, the UNet was only used, treating it as the best module for the image segmentation purpose. Later, it was discovered that many other modules like CenterNet performs better. Okay. So
No, I still didn't get. So, what is unit accomplishing here? If you remove unit, what would be the issue?
if I remove UNet, I won't be able to predict how much noise is there in each of the image. So unit architecture basically takes the images from different timestamps, and it basically tries to predict the noise in each image, and it keeps on subtracting the noise little by little in the backward diffusion process. Means how it is exactly predicting the noise, means what will be the value of that noise. We are going to calculate that in some later slides. So to summarize the flowchart, so note that we first converted the observed variables x into the latent variable z, which is easily processable, reduced dimensionality, etc. This conversion can be PCA or factor analysis or some advanced statistical methods like latent class analysis and structural equation model. Then we do the forward diffusion process to obtain some noisy images which are combined with other timestamps and fed into the unit module. Then we perform the backward diffusion process and obtain the reconstruction finite image using a decoder. So before diving deep into the math of how it works, so let us just try to run our code on Colab. So it would take some time to run, but let me show you the outputs first. So I have created 3 parts of this notebook, which goes progressively higher. Part 1, which installs some predefined libraries and predefined pipelines, as well as the weights used will also be pre-trained here. So we just import that. We import torch, and from diffusers we import the pipeline, and then we just work with that. We give a prompt, and we suppose the prompt is a duck made of glass and image of prompt 0. So this is just fetching out that image. So we can do from the Delhi OpenAI's website, we can just do a one-to-one comparison of how exactly that works. A duck made of glass. So it will take some time to execute, and you will find the results here slightly better, quite better. This looks like a glass, and we are not doing quite bad here also.
So
Okay,
this
so
pipe thing here, what is pipe?
the pipeline module, which I have already installed, means the
Or
pipeline consists of that encoder, decoder, everything, the unit architecture.
see,
So
basically you are using 1.4 SD. So if
yes,
you
yes,
were to use the latest 2.x SD, maybe it will do better.
yes. Actually, 2.x it uses like I have to check out its installation procedures and stuff,
Yeah, yeah.
and like we'll try to do it in some of the future webinars. So this is the output, and then what we do, okay, so we can get n number of images. So here I have tried to write the code for defining an image grid, and then it basically gives n number of images. And then in part 2, what I have done here, I have already created, I have already installed a predefined pipeline. Here I am creating the pipeline by loading the VAE tokenizer and the unit modules, as well as the decoder, and I'm just applying it. I'm defining the dimension of the images, and this is also this here I'm working on the prompt from earlier, a glass spaceship landing on water. Suppose this is the prompt, and we tokenize the prompt, and we define positionals and text embeddings. Actually, this detailed version of the code, detailed explanation of the code, you will only be able to understand. I will come to this code later after going through all the math, and then things will be really clear. Now,
So in this part 2, we are not using the SD pipe, right?
yeah, no, we are not using the pipeline, but we are using pre-trained weights.
Okay, of
In
SD.
yes, of the unit module.
Or UNet, okay. Okay.
So we are using the pre-trained weights of the autoencoder also stuff, and like here the parameter of the decoder is also defined earlier on. So we do that, and we can produce an output of the image, a glass spaceship landing on water. So we are quite doing, I guess we are doing quite decent here also. But after this, in the part 3, I have tried to implement neither the pipeline and nor the weights will now be pre-trained, but the complete thing will be done from basic PyTorch. So what happens in the forward process? So we will come into the detailed explanation of this code later. I am just now giving a high level overview. So we load some images of cars, and here we use image to image classifier, not exactly classifier, conversion. And then we use the torch.nn functional, and we use some functions which we create. I will explain you the math behind all this, and then only you will be able to understand this mathematics, why exactly we are doing this. And then after doing the transform, we transform the data sets using all those stuffs, encoder, decoder, and we also apply the unit module. So first we are doing the noising in the forward process. So you can see the output here. And then we create, using NN module, we create convolutional module networks, basically the basic structure of a unit network you can easily create. And sinusoidal position embedding, I will try to explain how this matrix works in some of the later slides. There is some positioning embeddings too. Then simple unit modules have the layers defined, and then we just give an object, create the class of the model, and then we can just do the training operation. So since this is from very scratch and I'm using the free version of Colab, so it took me 12 minutes to run just 3 epochs. So using the pre-trained modules and the pre-trained pipelines, things were much faster. So we would be generally using this, but to understand a deep overview of how exactly the stable diffusion model works, how we can tune the parameters to exactly improve our output, we need to understand the entire thing. So I will come back to this code at some later point. So let us just now start with the math part. Okay. Okay. So this is our forward process, which consists of the initial image x0, which goes all the way to xt. Now, as I told you, xt is the complete noisy image, which is completely normal distribution of 0, 1, which means mean of 0 and variance of 1. We will see that later. Now, the symbol which we will use to denote the forward process would be q of xt given xt minus 1. And now you must notice that I am using the x and z a bit interchangeably. These are not the observed variables, these are the latent variables. So the latent variables are actually easier to compute with. So we will take the latent variables at every timestamp, and we will just proceed with our forward function. So q is a mapping from xt distribution to xt minus 1. And we will use this q mapping for the forward process throughout our presentation. Now the backward process would consist from xt all the way up to x of 0, and xt being the complete noisy image. Now, while fitting our module unit model, we can also see that we can take x at different timestamps. So here, during the derivation of the formulas, I will assume that I'm completely going from noisy image. You can generalize that for any time t, although. So throughout this slideshow, we will also take care that our this p means the backward process and q means the forward process. So as the backward process will only depend on xt given xt minus 1 given xt. So you can do an observation here, is that at any timestamp t, let's say for the forward process I'm assuming, at any timestamp t, the variable is only dependent on t minus 1 and not on anything else, because t minus 1 is produced only from t minus 2 and so on. So this defines what is known as a Markov process in statistics. So let us just review of what our symbols mean. This is basically the backward process from xt to x0, which is denoted by p of xt minus 1 given xt, and the forward process would be defined by q of xt given xt minus 1. And the diffusion models have recently showed a remarkable performance in image generation tasks and supersedes the performance of GANs on several tasks such as image synthesis. This is due to the ability of the diffusion model to preserve the semantic structure of the data, about which we have already talked. So now the forward process. So as I told you, to be noticed at any timestamp t, the distribution of xt is only dependent on the distribution of xt minus 1. So this follows a Markov chain. So we will try to write the total distribution q from 1 all over to t, given we only have the x0 image. So this will give the total distribution of the corrupted samples given x0. Now from the property of the Markov chain, we can basically multiply all the way of t from 1 to capital T. That is our last value of the latent variable. So this can be the product of the single step conditionings or mappings. So this is a property of the Markov chain which I have used to get the total distribution of the corrupted samples, given that we only have x0. So in some later portion, we will also see that we can directly calculate the value of q at xt by using some mathematics. So now we are trying to find a distribution, a distribution of how things are related to one another. So from the basic relation of mean and variance, we can say that variance of x equal to expectation of x square minus expectation of x whole square. So here expectation means mean of x, and expectation of x square means mean of the variable x square. So we can clearly notice here that mean of a variable can be given by an under root term minus variance x. So the mean and variance are related by such a square root term. Also, since it is a Markov process, the mean of xt is also dependent on the previous distribution xt minus 1. And not also, is only dependent. And also dependent on the current variance, we can say. So what are the two things we can take away from here? Firstly, by such a square root terms, we can find the mean using the current variance. What actually in our timestamp t, what two data we are having? We are having the current data and the previous data. So from the current distribution of variance, and we are trying to basically find the mean. From the current distribution of variance, we can say it is related by such a square root terms, and we also know that from the Markov chain, it is dependent on the xt minus 1 term. So for a Markov process like this, we hypothesize the mean of xt to be something square root of 1 minus of beta t into xt minus 1, where xt minus 1 is the distribution at the previous timestamp and beta t is the variance. And we will find that this indeed is the mean for a Markov process. So for a Markov chain, in case of a continuous data, the transition is given by a diagonal Gaussian, which is basically a normal distribution of the random variable xt. And we just now found out that this is the mean of the function, just now derived from intuition, and this is the variance. Since beta t can be a matrix, I have also multiplied with an identity matrix, and this is the variance matrix at time t. Now this can be viewed as how much noise we want to add in the next step with respect to xt minus 1. So from going to xt minus 1 to xt, we are adding some noise. So we are corrupting the image. Mathematically, what we are seeing, the mean value which was earlier xt is now converted into 1 root over of 1 minus beta t. So we are multiplying this factor to corrupt our image. So this term can be viewed of how much noise we want to add in the next step with respect to the previous step. So also generally, beta 1 less than beta 2 less than beta 3, where each term lies in 0 to 1. So it is quite obvious from this that beta variance has to be positive and it has to be less than 1. Otherwise, the square root term will be negative. And we also take beta t to be greater. So as you can see, if we increase this beta t, this term will get reduced and we will be adding more noise, because a less term when multiplied with another matrix basically reduces the matrix. This term will be less than 1. The more less it is than 1, it will be able to reduce more. So we basically add, as we keep on this is the reason why we keep on increasing beta t. We increase beta t, this term will reduce, and then we will be adding more noise. So if we increase beta t, we will be adding more noise, and it is suitable that when we have lost most of the information from our image, that is in the almost the last timestamp, we are adding the maximum noise at that position. And initially we are interested only in adding little noise, and then we will keep on increasing our noise of beta t, which should be maximum at beta t. Because if you visualize the second last latent variable, xt minus 1, that is very close to complete noise. So we won't actually get much from that. So we want to quickly reduce that to complete noise. So that multiplier factor beta will be highest there. Okay. So continuing with our forward process, we have seen how this Q represent the forward process, and we have seen how the forward process basically represented by a normal distribution of the previous and the current values. So one thing which we need to understand from intuition here is that as t tends to infinity, it means that we are very slowly adding the noise, and at some point infinity we are having complete noise. So that would mean that beta t is less than 1. So it means that if beta t is less than 1, this square root term is very close to 1. It means that we are denoising the image very slowly, and then the mean of t approaches xt minus 1. This term is the mean of xt, right? And if this square root terms becomes very small, becomes close to 1, then the mean of xt would approach xt minus 1. Also, more beta t means more corrupted image. So from, let's say, so from this thing, it is clear that we add the least noise initially, and close to complete corruption, we add the most noise since it contains the least information. So this thing I explained you in the previous slide also. So also Q of xt of the final image is complete Gaussian noise. I've told this in some of the initial slide that complete noise is nothing but a normal distribution of 0, 1 for t equals to infinity, which is the standard Gaussian noise. So after understanding the complete math, I am sure we will be able to create some interesting prompts by really logical intuition. We will see that later. So now, as of now, bear with me.
Yeah, basically we are using what we call as a Gaussian probability distribution, or
Yes,
also called standard normal distribution, which is
yes,
defined by a mu, the mean mu and variance v, right? So that is
yes,
the formula, that n you see there. So that the first term is, I believe, the average mu, second
yes,
term is variance var, right? For a
yes,
Gaussian probability distribution. So that's how you represent a Gaussian probability formula, and
yes,
essentially you are adding noise in a forward progression, forward process, and that is counterintuitive. Why would you corrupt an image? You corrupt
yeah,
an image so that you can then train it how to uncorrupt from noise and
yes,
bring it back to image. So the idea is to create junk and then train it to produce image from junk. So,
yes.
so that's
And
essentially what we are doing.
yeah, like I can collect the noisy image from different timestamps, and the prompt, the text prompt which we enter, that also will contains various words, so that all of those words will signify some of those images which will which whose timestamps corruption will also be fed to the network, and then everything will be those will be combined using some attention modules, and then we will denoise them. So for this forward process, it is also necessary to keep a track of how much fast the noise is added. This is because adding noise too fast is also undesirable, as the generated image that will then be of low quality. As I told you, as t, we give more t, more slowly the forward process will take place. So we take care of this using a noise scheduler. So what basically happens is that it is possible to directly calculate the distribution at any timestamp t. let's say x of t. Now we had seen that we are calculating xt from xt minus 1, but for a Markov process, it is possible to directly calculate xt given that we already have the initial image. So we can directly use that formula. So what basically happens? So I am defining few terms here. As you see, we will be adding the noise. Here we linearly keep on increasing to add the noise. That is linearly increase beta. Okay, so beta value is increased linearly. And the alpha value is also decreasing as we define basically alpha as root over of 1 minus. Basically, we define alpha as 1 minus beta. You can see that alpha plus beta equals 1 at every timestamp. We define such a variable alpha, and then we define alpha bar as the cumulative multiplication of all the alpha. So alpha 1 bar will be basically alpha 0 multiplied by alpha 1. Alpha 2 bar will be the cumulative multiplication of alpha 0, alpha 1, and alpha 2. So we are just defining few terms here, and this is the formula which I was talking about, which we are going to derive, of how this q timestamp at t depends only on the initial image. We can calculate using this formula. So for the forward process, we can use something known as a parameterization trick for a normal random variable. We saw that the initial normal distribution was something like this. Now using the parameterization trick, we can directly write that this is the mean plus some root over of variance into epsilon, where epsilon is the normal variable of 0, 1. Now if you try to think, why does this actually work? So you can write this as mu plus root over of beta t. This works clearly because of the mean of q of xt given xt minus 1 is same, and using the property variance equals to b square variance, the variance is also the same, right? So if you calculate what is the mean of this term, which is 0, and what is the mean of this term, is this term itself, which is the mean, which is again equal to our previous distribution. Now what is the variance of this entire thing? The variance of a plus bx is given by b square ax. Now it is basically b square into the variance of epsilon, and the variance of epsilon is 1. So basically root over of b square into 1 is again giving us the same variance b. So that's the reason why we apply this parameterization trick, and now we will use this distribution to apply it everywhere. So for the forward process, we now initialize, as I told you, alpha t as 1 minus beta t, and alpha t signifies how much information we keep while transition from one image timestamp to the another. We also define alpha bar t as the cumulative product of alpha t. Now the q distribution of xt given xt minus 1 can be written like this due to our parameterization trick which we used. The same expression I've written again, nothing new in that. And now replacing by alpha, it will be something like this: 1 minus, we just replace beta t by 1 minus alpha t. And now to get the other timestamp, we replace t by t minus 1. So we get q of xt minus 1 given xt minus 2, and the alpha value will also, the subscript would also change accordingly. Also for a Markov process, we told you that xt minus 1 is only dependent on the previous timestamp, and also we saw that it depends on root over of 1 minus variance, so it depends on root over of alpha. So for any Markov process, a variable xt minus 1 can be written like this. So we now substitute the value of xt minus 1 in equation 1. So this was our equation 1, which we just obtained by replacing beta t with alpha t, and we substitute this value in this initial equation. This initial equation, we substitute the value. So we get this equation with just simple multiplication. And if we keep on doing for the successive timestamp, we will also notice that for, suppose, let's say here it's xt minus 2. What if it depends on xt minus 3? By simple substitution, you will find that it depends on the root over of product of alpha. till all the way till just before that timestamp. So this term we will replace by suppose dot dot dot, because it will be a quite large term, and this xt minus 1 coefficient is only this. On similar successive substitution, we will obtain this, as I told you, xt minus 1. So why are we doing all this? One second. So why are we doing all this? We basically want to calculate this value, xt of given x0. So we directly want to jump to our noisy image without going through all the process, because we will have many images, we have to combine many things, we have to do a lot of work. So we can't just do every step iteration wise, right? It will take a lot of time. So we are just shorting out our process.
But during training, you will actually train through successive noise additions.
Yeah, we will add the noise successively, but we can predict, but during when we feed it to our model, means many times we will be requiring to find what will be the timestamp at t, what will be the noise at directly the noise distribution at t. So we can jump to 1 0 to t, or maybe some alpha t, or maybe some small t to capital T directly using the formula.
Okay.
So that's why basically we are doing this. So on similar successive substitution, we can see this. So did you remember I defined something known as alpha bar, which was the cumulative multiplication of all the alphas. So now this alpha bar comes into picture. We can just multiply all the alpha. So root over of alpha bar of x0 plus some terms. Now we need to find this, what are those sum terms, like we can't multiply all over, so we are just trying to shorten. So we define some other variable beta t bar, which is equals to 1 minus alpha bar of t. Now by analogy, you already know that I had, by using the parameterization trick, I clearly explained how the normal random variable of this Gaussian distribution is parameterized like this. So using that parameterized trick, we can do this. Now you can notice some pattern over here. If we replace beta t by beta bar of t, what would happen? We can replace this thing here also. So you see, we have just found out that, right? So this beta bar of t can now again be resubstituted with this alpha bar of t, 1 minus alpha bar of t. So we will then get this final formula. So therefore, on resubstitution, we derived this equation. So we directly calculated the distribution basically at any timestamp q of t given x0, or given this, not necessarily 0. I showed you for 0, but for any timestamp to any timestamp, you can directly jump. So now we come to something known as batch training. So as I told you, suppose I want to create a really nice artistic car. So how that actually happens? Suppose at t equals to 250, I have image of this car. At t equals to 76, I have image of this car. And then for t equals to 30, I have image of this car. So we may be requiring many images. And those images, all of the timestamp is obtained by successive adding of noise. But we given the time t, if we want to select some noisy image of those particular time t, we can jump directly from image into that time t, and then we will just feed into the module. The batch training is done something like this way. So now for training, we feed the images from different timestamps into our neural network model, which is UNet. So here, after denoising, we are expected to get some new type of artistic car. So if we feed all this into the model would predict the noise, and then if we subtract we are also using the attention modules to combine all of these images, right? So one combination of images, and we will basically find the combination of all those noise, as well as basically the combination of, suppose these two have some noise, we will find the combined noise. We can find the combined noise of these two. So there can be various strategies. We can find the combined noise of single this picture also, and then we can just subtract those noise to get some new type of artistic car. So let's from our existing knowledge, so let us just try to produce some interesting results in the image generation. So one thing which I need to say is that after all this discussion, can you tell me something, some prompt which any SD module will not be able to correctly calculate? So as you see, this prompt is generating some images. We are denoising those images, and then again we are just going back. So what if I write something abstract, like something riding something, but then again that verb also will give correct output. Let's say, for example, I already showed you in my code that astronaut riding a horse. So basically our model knows what an astronaut looks like. It also knows what riding a horse looks like, and it is able to denoise and combine those both by preserving the semantic information of our data. So are we able to find some prompt or some word which basically cannot be imagined by that model? Let's see. What if we write something like a basket of 10 apples? What if we try to generate this? So it will take some time. So as you can see, there are not necessarily 10 apples. There are a lot of apples. So basically why does the error happen here? The model doesn't know how 10 look like. Does 10 have a face? No, it doesn't really have a face. So it is trying to combine basket, it is trying to combine apples, and it knows that I have to combine some number. But how does that number exactly look like? The model is unable to predict.
But Mitadru, this is trained on generic internet data. So
Yes.
it should know the semantic meaning of 10. That it should be 10 in number. It doesn't know that information?
No, actually what happens, the word 10 can have many semantic information. For example, semantic means what? The space around which the data covers. For example, the semantic information of an apple may be something small, and the semantic information of something else may be uh, big looking. So we can keep the apples side by side to create some bigger fruit. But since it's like that's basically the reason that it is not able to visualize how 10 actually looks like. What is the semantic information of 10? Because just using semantic information, we can't do that really, because a lot of a lot of other shaped objects may also be there, and which may be like some 10 apples may create some bigger fruit which is only one fruit. So the word semantic in the use of numbers is quite dubious. That is why the model is not able to understand.
Hi,
So
Bismillah. Any thoughts here? Bismillah, here.
Yeah, wait, yeah.
So why is it not picking? It doesn't know counting, like the letter 10, digit 10, word 10. Because 10, it has not learned counting and logic then, huh?
Yeah, correct.
So if I were to say a room full of 100 people, so it will not be able to produce 100 people, huh?
not exactly
Yeah,
100. It will give some number of people. It knows
Right.
that
yeah,
100 is a number.
Yeah.
That is what it knows. All.
Right.
yeah,
Right.
it's not able to count. But probably if you put like a basket of green apples, then it will
Yeah,
change the apple to
that
green apple.
yes.
So
But
Bismillah,
not,
this is using SD is using clip algorithm, right? OpenAI clip. So in clip, it has embedding for text versus images, correct?
mm,
So in that, it has not learned counting and logic words, huh?
yeah, I think so.
Okay.
So, so it will not also maybe uh, give more of spatial relative spatial positions, like, so if you give some relative spatial position within your prompt, probably it might not also pick up that correctly.
So when I say two people standing at a distance of 5 meters from each other, it will not.
Yeah, yeah, that
No,
I
no,
think it will not do.
it will not be. So actually, by spatial information, I think this is what he means. Let's just try one thing. A cat to the left of a dog. Let's see.
Left, it will not detect. Okay.
Let's see.
So there is one more question. Meanwhile, plural versus singular. Will it detect that? Plural versus singular.
Okay, so that's what. So maybe plural versus singular. Maybe it knows what adding s means to the word.
Mm-hmm.
So basically, it takes each of the word and visualize it from
Mm-hmm.
internet data. So if I think it may be done. Okay, I will just try writing an apple and then see for apples. So cat to the left of a dog. So this is the cat is to the right of a dog. The spatial information is also wrong. Cat to the left of the dog. Here it is correct. Here it is wrong. Here the dog is not completely visible, and here the cat is again to the right of the dog. So yeah, the spatial information is also.
Right.
So another thing which I noticed here, it is basically just combining words, right? What if we write cat dog? Once again.
Maybe in future versions of HD and Delhi, they'll solve these logic issues.
Yeah, so many times if we find here, some of the dogs also may look like a cat.
Right. Right.
Yeah, see this, for example, this dog.
Hmm.
It has some paws of cat-like cat-like structure. So basically, it is just combining images. And there are also some intermixing of results are there. So yeah, we will also be going through the code.
Yeah, new versions of these algos are coming by the week nowadays. So
Yeah, like
maybe in
one
couple
year
of
ago, nothing was there.
I mean, you see almost daily some new announcement on some large language model or image model. So I think in couple of months we should have some of these solved.
Yeah. So, sir, can we like call it a day since we had a lot of math and stuff?
Yeah. So is this a logical stopping point, Mitadru?
So, we are now acquainted with our forward process, how the overall working works in this way, and now we'll also see how exactly the backward process works,
Mhm.
how the timestamps are encoded in some of our future webinars, maybe.
Right. So we do need 1 more hour, right? So it will not be done in 10 minutes. So
Yeah, if I start a topic, it will like
yeah.
go on.
Okay, sounds good. So we'll stop here for today. We'll continue in a part two webinar, maybe in a week or two. Meanwhile, we can open it the floor to the questions. So uh, you can also try our CellStrat has an SD product, which is basic, not very advanced yet, but we are working on this. So so we have an SD product which I'm sharing the link. You can try this. And so this generative AI, both for text and image, is a huge new area for all of us to research and learn. And it has opened new paradigm around prompt engineering and fine tuning. and you can see some of the still gaps even in the Delhi 2. So was that Delhi 1 or Delhi 2, Mitadru, you were showing?
So that was Delhi 1.
Okay. Did you try Delhi 2? Does it solve some of those issues?
I don't think so that is means Delhi 2 and stuff. The Stable Diffusion 2.x is dealing with like 3D images and improving the like quality of the images and stuff. Like it's not something that special. It is improving the quality of image in painting and all.
Okay. So there's a question. If you see, there are some questions in chat.
Okay, sure. So 1 apple versus 10 apple. Yeah, that question also. An apple. Let's say. I think it should give 1 apple because let's see. I might be wrong. Yeah, so it basically it can differentiate between apple and apples. So it knows, I think it knows what adding s to a word means. It would look like more of those, maybe something like that. Yeah, so it works. Singular plural works. Okay. So what about words like text? What about words like text, please? Can you please explain what exactly do you mean by this? Meanwhile, we move to the next question. Can you please repeat why we jump to the last denoising image when we are teaching models functional noise addition? Can you please explain why we jump to the last denoising image? Okay, I got it. Just listen. So I told you that we are not exactly jumping to the last. So one thing what we are doing is that from one timestamp we are moving to the extreme last. If we do this from that initial timestamp, we can move to any timestamp t, right? So it's not necessarily last. I showed you here that like in the batch training, various timestamps are combined. So not necessarily we will take only the last one.
So for actual training, you will still do sequential training.
Yeah.
But for compute purposes, you want to derive that formula where you can jump from any time to any other time.
Yes.
Okay.
Any other test to image algorithm in study better than SD, or any enhancement planned in SD4? So any other text to image algorithm? So SD was only discovered 1 year ago in 2022, I think. So if it is there, I am not aware of, but I think it's not there because the SD is now also it's overpowering the power of generative
No,
adversarial networks.
Delhi, there are two big ones, like the Delhi from OpenAI and Stable Diffusion. These two are leading so far. Text to image.
Yeah, and also the Imagen by Google also there, but on the one-to-one comparison, I really don't if it
Okay.
actually leads
Imagen.
on.
Okay. Google Imagen. Okay.
Yeah, Imagen. Yeah, it's an interesting website. You can just see this. So from here, I have taken the screenshot of strawberry mug filled with white sisal. This is also like quite awesome. So, join the skyline with Google Brain, global it and Paras. This is what I have put in my presentation. Olympics. So yeah, it can create a large variety of image and also. So would it be possible for you to share the notebook that you have demoed today? Yeah, actually, I have not given. I have just given an overview, high-level explanation of the code. So I'm planning to after explaining the complete math, I'm also planning to explain what each section of the code means and how we can make better sense of it. How we can
Yeah,
tune the hyperparameter.
do you have this on your GitHub? You can share the GitHub link.
Yeah. I have that. I have that.
You can just provide the GitHub link.
Yeah. Yeah. So there is something known as Hugging Face notebook, and one of the YouTube video I used those to understand, and from there maybe most of the things of and some other websites also. I will point those out. Those I used to create this notebook. So Sumit, yes. So it has to be an abstract sense of number and just not just the exact counting. Yeah. Abs. Huh. 1 versus 10. 1 versus 10 because singular versus plural. I'm like the word itself is changing. The apple to apples, the word is changing. But like if you compare 2 versus 10, 2 is also apples and 10 is also apples. The word is not changing. So that's why it's exactly makes a mistake. That means what are we providing as input? Only the words, right? So it has to visualize how each word is different from one another if it is at all different. So in our next webinar, we will also so even with the same prompt, if you run again and again, you will get different result. So why exactly that happens, that also we will try to understand through our mathematics. Like, we like apples with different same prompt, we give different time, it will show different images, but why exactly? So how does it, why does it not show the previous images same to same? So we'll try to understand all those out too. So that will be requiring to understand in detail about the backward process.
Okay, great. Any other questions, audience? Okay, thanks, Mitadru. Interesting session, very nice. We'll set up your second part two of this, right? And then continue with other things like SD extension, Dream Booth later.
Yeah, sure.
Thank you all for joining. Thanks, Mitadru. Awesome.
Thanks a lot, sir. Thanks a lot.